All right, good morning, everyone. This is lecture 2 in the section of chapter 41 on quantum physics. This is a makeup lecture that was done in lieu of the March 19th lecture, which could not be filmed at that time. So I'm doing a makeup right now in case you want to view the material that we covered on that day. Okay, so let me review very simply where we stood last time, and we'll go from there. So there are two important aspects of quantum theory. One came from experiment, and one came from a theoretical paper. And we're going to write down what those were because they're the guiding principles of the quantum theory, and in particular, the development of the Schrödinger equation. So the two aspects that I'm referring to are diffraction of particles. So there were diffraction experiments that confirmed the wave property of particles. And the second one is the de Broglie wave hypothesis, where de Broglie hypothesized that particles have a wavelength or a wave property that can be described by a wavelength, that particles have a wavelength lambda, which is given by h over p, which he said is just like photons. So when you remember that when we did the section in chapter 40 on the photon nature of light, then we got this relationship that lambda is equal to h over p, and so de Broglie hypothesized that that particles would act like waves in the same way that electromagnetic waves act like particles. Now, up till now, we have not said anything about what the wavelength is with regard to. In other words, unlike light, the wavelength is not related to an electric field vector oscillating in space or magnetic field vector. At this point, it is uncertain as to exactly what that wavelength refers to. But you will recall that from last time that when we looked at the diffraction pattern of, for example, we had a double slit experiment with neutron beams, that when we looked at the intensity pattern, then we inferred or stated that the intensity pattern of the photons on the screen, so these were of the neutrons on the screen. This was actually an experiment done with neutrons of a particular wavelength lambda. And this was for neutrons. So the neutrons had a certain momentum, p, and I forgot the exact value which we could calculate from this relationship, but we confirmed that in fact it did give the correct location of the peaks. So you remember in double slit diffraction, d sine theta max, or theta 1 max, was equal to 1 times lambda, for example. And lambda was given by this value. Now I think I may have that. Give me 1 second here. The actual value of the momentum for this particular case was 670 eV over c. Okay? So now, having said that, we can write that the intensity function I of theta, or we could do I of y if you want, but theta, of course, being the angle of the particle from that would, in this case, would travel from the slit to the distant screen. That this could be written as the number of particles, let's say the number of neutrons per second, times the single particle distribution, or the probability function, which we will call P of y, right? And we said that in analogy with classical electromagnetic theory, that this function P of y could be written as the amplitude of the electric field squared that we, times some constant, we will say, for example, that it will be proportional to the amplitude of the electric field squared at a distance point theta on the screen. And of course, we also remember that if this is a distance L away from the slits, then y is equal to L times the tangent of theta. Okay? So we said then by analogy that if we were to do this with particles, what we would do is say is that the probability P of y with particles, so this would be, for example, in the neutron experiment, if we were using neutrons, would be given by the amplitude squared of the wave function. And so the wave function now means simply that it is the probability amplitude that corresponds to finding the particle at a distance, at a given distance y from the center of the slits. So this became the standard for which we view the wave equation, and having done this, then we can then say that I can now write down what I expect the wave equation to look like, because it will look very similar to the electric field equation that we did for electricity and magnetism. So in this case, what we would say is that the phi of 0 as a function of y, in this case, would be equal to or proportional to a constant times sine of beta over 2 divided by beta over 2. And beta is equal to 2 pi over lambda times d little d. I'm sorry, I'm doing single slit. My mistake. Give me 1 second here. Correct. We're doing double slit. This would be times c times cosine of delta over 2, where delta is equal to 2 pi over lambda times little d times sine theta, where little d is the spacing between the slits. Okay, so little d is the spacing between the slits, and we replace lambda as an electromagnetic wavelength with lambda as the wavelength of the particles, which we associate as a probability wave. In other words, there's no physical dimension of the or physical interpretation of the wave function, other than to say that it will predict the probability of where the particle can be found. So this substitution then would in fact, if I did this for these particular equations, and then of course I can relate that that tangent theta is equal to y divided by the distance from the screen, then I can write this as a function of theta. Okay, so the idea now is that psi, which we call this wave function, is a probability function, and it's related to the probability of finding the particle if I square it and I equivalence that in this way to a probability. By the way, to keep things consistent, I'll put a constant c up here as well, although the exact value of that constant may not be the same in these two cases. But the theta or y dependence depends in a similar way upon the amplitude. Okay. Well, how do I now want to express this theta sub 0, or this psi of theta sub 0? Let's do it in terms of the wave that we know. We know there's an impinging wave coming onto the screen. And so I can write that the wave equation for a traveling wave, psi of x and t, is going to be equal to some amplitude a times the sine of kx minus omega t, which I can also write in particle terms as we did in lecture 1 of chapter 41, to write this as px minus et divided by h bar. Right? And we said that we were going to use the complex form of an oscillatory wave function. We described that, the rationale for that last time, and what we said was we would write this as an exponential of of a times e to the plus I px minus et divided by h bar, and this could be written in terms of a real and imaginary part, which we write as a times the cosine of the argument. So this is px minus et divided by h bar plus the constant a times sine of px minus et divided by h bar, and there's a real part at times I, right? So we can simply think of this exponential as a complex. The complex exponential as being the sum of a real and imaginary part, both of which are either the sine or the cosine function. So this is what we end up with when we want to describe the probability distribution of a uniform stream of particles that have equal probability of being found anywhere along the x-axis. We need to use the exponential complex form rather than the simple sinusoidal form for the wave amplitude. Okay, so having given that description, we can now go back and or continue and talk about how we would describe a wave equation. So we want to actually develop what's called the wave equation. And we'll erase some of this right here. And we'll call this the wave equation for a free particle. Now this is in fact a wave equation, but it's a solution to a differential equation. And so what I really want is a wave equation that has psi as a solution, as psi of x and t as its solution. And it will become clear a little bit later, but basically we're going to find a differential equation for which I already know the answer. And you can ask the question, well, if you already know the answer, then why would you be making a differential equation that requires finding a solution? And the answer is because up till now, we're only dealing with a free particle. It's one in which there are no forces acting on the particle. Once I start to put forces implied on the particle, then this wave equation will no longer be the one we want, and we need to solve something more complicated to get the full answer. So we're going to start this, and this is sort of I think the way that Schrödinger actually thought about this when he was developing the wave equation that we are now going to describe, that is given his name attached to it. Okay, so and I might indicate that this is a differential wave equation that we're looking for, that has psi of x and t as its solution. Well, the path to getting there is not too complicated. What I'm going to write down now is that I certainly, for a free particle, I expect that p squared over 2m is equal to the kinetic energy, and in fact, in a classical system, that's equal to the total energy. So I have p squared over 2m, which is equal to the total energy. If I multiply psi by p squared over 2m, then that should be equal to the total energy E times psi, right? And psi is x as a function of x in time, space and time. So this particular equation will now allow us to move towards the Schrodinger equation. And the way in which I do that is to note that if I take the second derivative of psi with respect to x, and I multiply by minus h bar squared over 2m, then that second derivative with respect to psi of the wave function with respect to x is actually equal to p squared over 2m times psi. Right? And you can verify that simply by taking this form of the exponent. When you take the derivative of a form e to the ax, where, for example, you get a times e to the ax. So, and I do that twice, then I will find that I get a single power of p when I take the first derivative, and taking the second derivative, I get another power of p that comes into play as a coefficient of the exponential, and so I get a p squared term in here. And that's the rationale for showing, as you can do yourself, that taking the second derivative of this function, in fact, gives you p squared over 2m when I multiply it by the appropriate constant. Okay, so that's something you can do as for yourself as an exercise. But the upshot is that this substitution now gives me a differential equation for solving the what we now call as the Schrodinger equation. So it's minus h bar squared over 2m times the second derivative with respect to x of psi, and this is equal to the total energy E times psi. Right? Now, I'm going to generalize this. This is obviously, this term is related to kinetic energy because we said this part is equal to p squared over 2m psi. And we can generalize to what psi will look like in a force field by incorporating the potential energy. So now let us suppose that the particle is no longer free, but it is under the influence of an external force, and I can describe that force as given by minus the derivative of the potential with respect to x. Right? This is a function that you get, a relation you get from classical physics. Force is equal to minus the derivative of the potential. Well, we know that the total energy is kinetic energy plus potential energy, and that energy is conserved throughout the motion of a particle that is under the influence of an external force. And I can write that then as the kinetic energy term, which is minus h bar squared over 2m times the second derivative with respect to x, operating on psi, but I'll put this out on the outside in just a second. And I'm going to say plus u of x, which is the potential energy term, all multiplied by psi of x. And of course, by x, I mean x and t. And it's as equal to the energy E times psi of x and t. Okay? And this is, in fact, the Schrodinger equation. And oftentimes, we want to solve this for conditions or cases. We want to solve for cases where the total energy E, where E is equal to a constant for all time. In other words, it's in a state of constant energy, constant for all time. Okay? That's what we want to generally do when we solve the Schrodinger equation. Now, this equation, the Schrodinger equation, can be further simplified by the following assumption. I mean, it's actually a derived fact. It's not something that I have to assume, but I'm going to simplify it for us right now. That oftentimes in differential equations, that involve more than one variable. Here, of course, we have a variable that depends on position and depends on time. That I can write the equation as a product of a spatial dependent wave function, which I'll call little phi of x, times the time dependent wave function, which I will call f of t. Right? And in certain cases of differential equations, such as this Schrodinger equation, we can assume that the wave function factorizes into a spatial and a time component. Now, once we do this, and one can show, and I'm not going to do it here, that this function f of t is equal to a particular function that it can be written as e to the minus I e t over h bar. Okay? It's a simple property to derive, and it's done in cats if you want to look it up, but for now we'll just say that this is true. And also remember that we're talking about cases where a particle is in a definite energy state E. And that is an important part of this because we want to find different values of E that are satisfying this equation. So this is the root of the Schrodinger equation. Now, if I put this value of psi of x and t into this equation, it simplifies into a simpler differential equation, namely that minus h bar squared over 2m times the second derivative, and now it's no longer, there's only one variable involved, so it is simply a second derivative of psi of x plus u of x times psi of x is equal to the total energy E times phi of x. Okay, so this is what is called the time-independent Schrodinger equation. Independent Schrodinger equation. Okay, and we'll describe a little bit about what that means. But basically, the result of this solution is that the probability distribution of where the particle can be found does not change with time. Now, oftentimes we are going to be interested primarily in bound energy states. Bound states, bound, B-O-U-N-D. Bound energy states are ones in which the particle is trapped. So let's say, for example, a particle is trapped in a attractive force field, and attractive force field which means that the particle is not free to continue moving continuously out to infinity, but it is bound. A couple simple examples of that. One is, which we'll talk about in the first example, is a particle that is bound in a potential well. So in a potential well, such as the one I've drawn, the particle can move back and forth in this well, but due to the constraining forces on the edge of the box, it cannot escape this localized region of space. And we'll talk about the case where the particle is trapped between the x-coordinates of 0 and x-coordinate of plus L. And we'll talk about that, but that's a confined case. Another case of a confined case would be, let's say, which is not in fact a quantum system, but is an attractive force, is the planetary motions of the planets around the sun, the gravitational force, of course, holding them in their orbits. The Earth and the other planets are not free to dislocate and move out away from the sun, but they are trapped in a fixed orbit and they cannot move away from that. Similarly, the case of an electron in orbiting a positively charged nucleus is held by an attractive force, and we will be studying those as well. So these are cases that we're most interested in, and let's go back and talk a little bit about the time-independent Schrodinger equation, what that actually means. Well, if I use this expression for f of t, and I say that the probability of finding a particle at a given location x at times t is given by the square of the probability function psi of x and t, quantity squared, right? Then what I can find by doing this substitution is that this is equal to the complex conjugate of the individual wave parts of the spatial wave function times the complex conjugate of the time component of the Schrodinger wave function, and I am going to multiply then that by the wave function itself, which is psi of x times e to the minus I e t divided by h bar. Okay? And what I can see here is that if I multiply e to the I e t over h bar by e to the minus I e t over h bar, and I add exponents, then I get that this is equal to the psi star complex conjugate of phi times phi of x, okay, times the product of these two exponentials. But the product of these two exponentials is e to the 0, which we know is equal to 1. Right? So we then get that for cases where the total energy E is constant, and in fact the particles are held together in a bound orbit, that the probability function, the function does not depend on time. Does not depend on time. Okay? So this is the basic idea of the time-independent Schrodinger equation, is that I can eliminate the time component, and I can solve a much simpler differential equation. And furthermore, when I solve for that, I get the probability distribution, which is constant over time. So that means that even though we may think of the particle as moving around in orbits or confined in locations, from a wave point of view, which is the only point of view we have that will accurately describe the particle, the probability of locating it at a given position does not change with time. And that's a little bit hard to understand. For example, you might think that if I have a particle that is sloshing back and forth here, that the probability of finding the particle here is different in time versus the probability of finding it here or there at a later time. In other words, that the probability of knowing where the particle is depends on how far it has moved. It turns out that for solutions with constant energy, that is not true, and that the probability is in fact time independent. So we'll write this down as the time-independent Schrodinger equation. We're going to do an example of a simple solution to the Schrodinger equation that will be very, I think, informative. It is also an example that we will come back to when we discuss the theory of conductors. So it's actually one that is applied to different aspects, some aspects of electrical engineering, but we're going to do it in a more of an abstract sense right now. But the basic idea is quite simple. So the idea is that let us imagine that I have a particle that is trapped in what we call a potential well. And this potential well is one in which, as a function of the coordinate x, I have a potential energy function that is described by this curve, and I'm going to choose the x equals 0 coordinate to be located at the left edge of the box, and on the right edge is the other boundary of the particle, and in between the particle is free to zip back and forth. Right? hits the ball, hits the wall, bounces back, keeps going back and forth, back and forth, back and forth. Right? So the way I'm going to describe this potential is that we're going to describe it by saying that U, which is the potential, U of x, is actually infinite on either side of the boundary of the potential, and U of x is equal to infinity over here, and this will be for x less than or equal to 0. We'll call it less than 0. And this will be for x greater than 0. I'm sorry, greater than L. For x greater than L. So, and in between the region from 0 to L, we will have a condition where U of x is equal to 0 for 0 less than x, which is less than L. So that's the description of this. The height of the barrier is infinite. Means there is no way in which the particle can go beyond the boundaries of this wall. Now, what we are going to do is to use the Schrödinger equation to find out what are the different energy levels that are allowed. So we are going to find out that there are certain discrete energies, and by energies I mean 1 p squared over 2m, or what we also call as 1/2 mv squared. Right? So what this says is that the velocities of the particles are going to be fixed by certain amounts when they have to obey and follow the Schrödinger equation. So the Schrödinger equation in this case is minus h bar squared over 2m times the second derivative of, we'll call it phi now because we're doing the time independent Schrödinger equation, is equal to the total energy E times phi, and this will be a solution for x less than, located the value coordinate x of the particle between 0 and L, where L is the length of the box. Now this is, in fact, the equation that we just derived, and we're using it again. But what I can do now is to bring this over to the other side, this term, and rewrite the equation. I'll multiply through by the inverse of this coefficient, and I'll get the d squared of phi d by dx, and this will be plus 2me divided by h bar squared times phi of x is equal to 0. Okay? Now it's just the same equation that we had where we started with, where we had assumed that the equation for psi was an exponential, right? We assumed that it was equal to e to the I times px minus et over h bar, and I could write that as a times phi of x times e to the minus I et over h bar. And because this is a solution of constant energy, when I square this term is no longer relevant, but rather what I get is that the magnitude squared of psi is equal to a squared times phi of x squared. Now we had assumed in all of this, based on this identity, that in this form of equation, that phi of x is equal to e to the I px over h bar, right? That's a way in which I can write phi of x. And the solution should exactly be the same over here. Only now what I'm going to do is I'm going to write the solution slightly differently. By the way, I want to also point out that another solution to this equation, which I could have written, is e to the minus I px over h bar. And what this corresponds to is a particle moving in the opposite direction with the negative momentum, the negative x direction with momentum p, and that corresponds to the minus px over h bar, whereas the plus px over h bar corresponds to the particle moving in the forward direction. But the magnitude of p is the same regardless of whether the particle is moving in the forward direction or the opposite direction. Now, now we come to some elementary theory of differential equations that if you have not had, it's still worth you learning right now, because you will certainly have to learn it in your future courses. And that is that any second order differential equation, which is what this is called a linear second order differential equation. It means that it involves derivatives that are only up to the second derivative, that it has linear coefficients. So the coefficient of this term is 1. The coefficient of this term is EME over h bar squared, and this is called a linear second order differential equation. Linear second order differential equation. Okay, and a property of differential equations is that any second order linear second order differential equation will has two independent, we call them independent solutions, or linearly independent, or two independent solutions. And the most general solution is one which is a linear combination of both of them. So if I were to do this in exponential terms, as I've done here, for which we derive this equation, the most general solution, for example, would be psi of x is equal to, and I'm going to use different constants, but I'm going to call c times e to the ipx over h bar plus d times e to the minus ipx over h bar. And this is a linear combination of two independent solutions, e to the plus ipx over h bar times e to the minus ipx over h bar, with constants where c and d are constants. Right? So that's one way in which I can derive the spatial wave function. And again, this has to be true because I use this form in order to derive this equation. But there's another way in which I can express those solutions. I can express those solutions, and you can verify for yourself that a wave function phi of x equal to sine of kx, where k is equal to the square root of this coefficient, so it's the square root of 2me over h bar squared, is a solution. This is a solution of this differential equation. Similarly, I can show or assume that phi of x equal to cosine of the kx is also a solution of this differential equation. Again, k being given by this expression right here. And therefore, the most general solution that I can have for the second order differential equation is phi of x is equal to a times cosine of kx. I'm sorry, I meant to use sine first. Phi of x is equal to a times sine of kx plus b times cosine of kx. Okay. This is the most general solution of this second order differential equation, and I can express it either as a sine plus a cosine term, or I can express it as the sum of an exponential, one with a positive exponent and one with a negative exponent, but the argument otherwise of the exponent remains the same. So I can show that these two are in fact equivalent. I'm not going to do that right now, but basically the idea is that you expand out this e to the I px over h bar using the Euler relationship, and I will write that down briefly just to keep it in your mind that any function that I write that e to the I px with over any coefficient of I in this term can generate a equivalent expression which has a real and imaginary part, which is given by px over h bar plus I times sine of px over h bar. And therefore, when I expand this out, you can see that you get sine plus cosine in the positive exponent, and of course you could do the same thing here. And when you add these two together, you can see that you get a sine term and a cosine term, and such that if I add these two together, I get a linear combination of a sine function and a cosine function. Okay, I'm not going to go through all that right now, but we'll just simply take this as our general solution and see where we can go with that in order to generate what we find out in terms of the energy levels of the Schrödinger equation. Right? So one other point that I think is worth noting is that the goal or the way we use the Schrödinger equation in general is for two things. Remember, when we solve the Schrödinger equation, we're trying to find out for bound states, in other words, cases where the electron is trapped within a given confine, what are the allowed energy levels that the particle can have? And secondly, what is the probability of finding the particle at a given location? And that's given by the function phi of x. So the Schrödinger equation has two important things to look for. It has what is the energy E that's allowed by this equation, and what is the function phi of x that we solve for that's going to say exactly what is the probability distribution of finding the particle at a given location. Okay? So that's what we're trying to shoot for in every general case when we solve the Schrödinger equation, of which we're doing a very specific or special case example right now. Okay, so the idea now is that this is the general solution that we have. A sine kx plus b cosine kx is the general solution. Now let's see if we can find out a little bit more. Oh, one other point to bring out here, because these are infinite barriers, that the particle is trapped completely in here, we are going to assume, and not just assume, but use a reasonable assumption, that the wave function psi of x, or phi of x, is going to be equal to 0 anywhere outside the box. So over here, phi of x is equal to 0, and over here, phi of x is also equal to 0. Right? And only in here is where we are trying to solve for the wave function, where in fact it is not 0. Okay? So how do we go about doing that? Well, in order to do that, we have to solve, we need to know something more specific about how to calculate what is k, and how are we going to calculate what k is, and what are these coefficients a and b. So my function has three unknowns here, a, b, and k. Right? So in order to actually plot this out or do a calculation, I have to know what is a, b, and k. And of course, I want to know what the energies are. Okay. Well, the first thing I'm going to do is to use the fact that one of the things that we can say or look at is that the wave function, there are two boundary conditions. The wave function phi of x must vanish at x equals 0. So let us say that phi of x equals 0 must be equal to 0. We're going to assume that whatever the probability distribution is in between the box, that at the edges of the box, the probability has to go to 0 because the particle cannot be found anywhere outside beyond that. And we will assume that that the probability of finding the particle at 0 is the same whether I approach the probability from the left or I approach the probability from the right. And the boundary condition is that the wave function has to vanish here and has to vanish here. So the two boundary conditions I have is that phi of x equals 0 is 0, and phi of x equals L is also equal to 0. So the wave function has to vanish because, why? Because the probability at x equals 0 must be equal to 0, and the probability at x equals L is equal to 0, And this is simply given by the square of the wave function. So you remember that in this scenario right here, that or the way we've identified the meaning of the wave function, phi of x, p of x is equal to the magnitude of phi of x quantity squared. Okay? Also keep in mind that my notes on complex variables, on complex numbers, are given in this handout sheet, which you should have gotten a copy of. And for simple expressions, particularly where, well, in general, we can write that this is equal to the complex conjugate of phi times phi. But if, in fact, these wave functions are real, this is simply the square of the wave function, psi of x. And we're going to find out in this particular case the wave functions of phi are in fact real, and we will find out exactly how to calculate them. So the first thing I want to do is to apply one of these boundary conditions. So let's apply the boundary condition that at phi x equals 0, we get that we evaluate what this means. So what is phi of 0? Well, I got to put 0 in here, right? So this means that phi of 0 is equal to, well, the sine of 0 is 0, right? So this term is no longer here, and so this becomes b times cosine of KL. And this has to be equal to 0, right? I'm sorry, k times 0. So the value of x is x equals 0. The value of the cosine, we know that since the cosine of 0 is equal to 1, that this must mean that b is equal to 0. Right? So b equals 0 is one of the boundary conditions that comes out, and now we know that our wave function must be of the form phi of x equals to a times sine of kx, right? So we've already gotten rid of one of our constants. We still have two more we have to deal with. We need to know what is k and what is a for values that I need to solve, that I want to solve for. So for that, I need to use the other boundary condition. And the other boundary condition is that this function evaluated x equals L, phi of L, is equal to a times sine of KL. And we know that this must also vanish because the probability must vanish at the edge of the box. And so we get the condition that a sine KL equals 0. So now I can ask the question, what are the values of KL such that the sine is equal to 0? If I have a condition that sine of KL is equal to 0, right? Then what values of KL will be allowed by this? Well, I can have the case, we must have the case where KL is equal to 0, it's equal to pi, it's equal to 2 pi, I'm sorry, it's equal to 1 pi, I already did that, 1 pi, 2 pi, 3 pi, all the way up to n pi. So any multiple of pi will work. So in general, I can say that k times L is equal to n times pi. Right? Now, I'm going to state probably without proof, but this is something you can verify, that if I have the case for n equals 0, which is one of the conditions, or we should say that KL equals 0, then we can show that the energy E is equal to 0, and also that the wave function psi of x is equal to 0, which means that this is what we would call a pathological case. This is a case where a pathological or non-pathological solution, and it's one in which is not allowed, because if the wave function was 0 everywhere, then of course the particle wouldn't be anywhere in the box, and we would then have a solution that does not make sense. So we're going to use the ones in which KL equal to n pi, n is equal to 1, it can equal to 2, it can equal to 3, all the way up to infinity, right? And so what does that mean in terms of the total energies available for the particle in the box? Well, what it means is that if I do this substitution, and I'll do that over here now, on this side of the board. Over here now, this side of the board, that I can do the substitution that the square root of 2me over h bar squared times L is equal to n, any multiple integer n times pi. Okay. Now I square this and solve for e, and I get that e is equal to let me see if I can do this right. E is equal to, solving this for e, is equal to n squared times L squared. I'm sorry, E is equal to h squared, n squared times h squared, times 8 times the mass of the particle times L squared. Okay. And I'm going to put a subscript E in here because this will be for the nth energy level. So basically now what comes out of this is that the allowed energies for a particle in a box, E1, is equal to h squared over 8mL squared. The energy allowed, the energy level L2, is given by 4 h squared divided by 8mL squared. And the energy E3 is going to be given by 9 h squared divided by 8mL squared. Okay? So those are the allowed energy levels for a particle in an infinite potential well. Now, it will be useful to do some calculations with this, so we can do some simplification to convert these to units of energy that are that we can use for calculations. So what I'm going to do is to calculate the energy E1 in terms of electron volts. So let's do this by electron volt. So what I'm going to do is I'm going to substitute I'm going to write out this equation for E1. I'm going to multiply the numerator and denominator by c squared, and that way I can express the mass of the particle in electron volts, where E equals mc squared. So I get h squared c squared divided by 8, and then this is mc squared divided by L squared, right? And I'm going to do some substitutions. One of the substitutions is that, as we looked at or saw last time, that H times C is equal to 1240 EV nanometers. Right? And you may remember this combination as one in which we calculate the energy of a photon, right? We said the energy of the photon is given by hc divided by lambda, which of course was h times the frequency, right? So we've encountered this constant before, and furthermore, I know what the so we will assume that m is equal to the electron mass, and so for the electron mass, I know what that is because I know that m electron times c squared is equal to 511,000 electron volts, right? So that will be very useful for that. And now I'm going to assume that I'm dealing with dimensions where L are multiples of 1 nanometer. So let me evaluate for L equals 1 nanometer. And if I want to use it for a different number, I will simply put in the number of nanometers here. But now I can find a way to evaluate this. And so this becomes 1240 squared divided by 8 times 511,000 squared times 1 squared, and I get a result that this is equal to 0.376 electron volts. Okay? So what does that tell us? It says that the ground state energy, by the way, this number right here, this is the lowest energy state, and the lowest energy state is referred to as the ground state. Sometimes it's called the 0 point energy, or they'll call this the ground state energy, or you will see this in your problems as written as the ground state energy, or sometimes it is written as the 0 point energy. 0 point energy. It's the minimum energy available to the system. Okay? 0.376. So that's one way that we can describe that. So now I know that if I were to do the n equals 2 case, I would multiply this by 4. If I would do the n equals 3 case, I would multiply it by 9. And I can find the energy levels for the other, for the electrons in the higher energy states. Now in general, L might not be equal to 1 nanometer, it might be equal to 4 nanometers or some other number. So the way I can generalize this now for the nth energy levels, and this is for electrons only, and I would get that this would be equal to 0.376 EV times the times n squared over L squared. So n squared over L squared, and this will give me the energy of the particle in the nth energy level. Now notice that because this is kinetic energy, once I find out what this value is, I can equivalence this to 1/2 mv squared, and as long as it's non-relativistic, which in many cases it will be, but of course eventually it will become relativistic, but at the lower energy states we would expect, in most cases, this would be equal to 1/2 mc squared times v over c squared, and I can solve for v over c once I know the kinetic energy. So that's one way of getting using this. It's finding out what kinetic energies or what velocities are possible for the electrons in the different energy states of the system. So this is the part one of the solving of the Schrodinger equation. Remember, anytime we solve the Schrodinger equation, there are two things we want to know. What are the allowed energy levels that are given, that are allowed by the wave equation, which we have now done to find out what values of E are possible, and what is the wave function, psi of x, which describes the probability distribution or function of the particle. Well, we've now taken this to the level where we now know what the values of K can be. We can see right here that from this boundary condition that KL is equal to n pi over L. So now what I can do that say that in general this becomes psi of x is equal to A times the sine of K, which is n pi over L. So this becomes n pi x over L, right? And that is a solution, and now the only unknown variable that I have, and by the way, I will put a phi sub in here because this will be the wave function for the nth state corresponding to the nth energy that I derived over here, or E sub n. So E sub n gives the energy for that state, phi sub n gives the wave function, and of course the probability of finding it in the nth state is px squared, which in this case will be equal to phi squared of x. So this gives us the probability distribution of finding the particle at a given location x inside the box, and of course this is true for 0 less than x less than L. Okay, so that's what we have as a solution. Now, the only thing we're missing in order to actually calculate a probability is what is the value of A, right? The value of A now can be defined by the another condition on the wave function, and that is that we know that the probability of the particle being somewhere, of particle being somewhere in the box must be equal to 1. It must add up to 1, right? The probability. So we can do that and apply that particular condition and see what we get for the constant A. So the equation for probability says that the integral of the probability P of x dx from x equals 0 to x equals L must be equal to 1. Right? That is to say that the probability of the particle being in the box somewhere must add up to unity. So I can now do that because I know that the probability is the square of the wave function, and the wave function is A times the sine. So I'm going to square the wave function, and I'm going to put that in for the probability. So this becomes A squared times 0 to L times sine squared of n pi x over L dot dx. And this has to be equal to 1. Now, you can show fairly simply that this integral, you can evaluate this, and that you can show that independent of what n is equal to, the value of this integral is equal to L over 2. Okay. So this says then that if I want to solve this, substituting L over 2 in for this integral, I get that A is equal to 1 over the square root of 2 over L. Okay. So now I have the full solution, and that means that phi of x is equal to the square root of 2 divided by L times sine of n pi x over L, and I have my solution. So this is the solution to the wave function. So now, in addition to finding what the energies were, I can now also find out what the wave functions look like. I can plot these for n equals 1, and n equals 1. I can plot it for n equals 2, and I can plot it for n equals 3. So let's put this here. 5x, and this one right here is going to be n equals 3, and I think I will actually put this n equals 1 closer in here as well, because we're now zooming in to the solutions for the particle in a box. And what I find when I plot this is that the first solution for n equals 1 is a half-wave sine function that looks something like this. The solution for n equals 2 is a complete sine wave function that looks like this. The solution for n equals 3 has 3/2 of a wavelength, so it looks like this. And I can keep going up, and every time I go up, I get to a shorter wavelength solution that increases in value, or decreases, the wavelength decreases as I go up to higher and higher energy states. So this is essentially what I have, and I can show that lambda for each of these cases is equal to n divided by 2L. I'm sorry, 2L divided by n. So lambda decreases as 2 times L divided by n. So n equals 1. The wavelength is equal to twice the length of the box. for n equals 2, the wavelength is equal to the exact dimension of the box. For n equals 3, the wavelength is 2/3 the length of the box, and so forth. So lambda sub n is equal to 2L over n, and the de Broglie relationship still holds, so this is equal to h divided by the momentum of the particle. Right? So I can still use the de Broglie relationship as well as the boundary conditions on the wavelength to find out how the momentum is quantized for these different solutions. Okay, so that is more or less in a nutshell what we have for the energy levels and for the wave functions. I will only add one more comment to say that what I'm mostly interested in here are the solutions where, or to know what the probability is. So that if I want to know, let's draw out for what these probability functions will look like, and then we'll discuss more about that in the follow-up lecture. So in this particular case, if I redraw this graph out, and I now, instead of plotting the wave function, let's say I want to plot the probability, P of x, of finding the particle at a given location, then what I'm going to do now is to plot out the square of the wave function. So P of x is equal to phi of x squared. That's the square of the wave function. And when I square the wave function, then what I get is these are allowed values E1, E2, and E3. And now it's very simple. When I square a negative portion of the wave function, it becomes positive. And so the shape of the wave function of this one stays the same. Notice that the sign peaks in the middle. And so that stays the same. This one, the probability wave function, becomes like this. And the third one, the probability distribution, becomes like this. Right? So the interesting point about these going up is that even though there's a particle in a box going back and forth, there are certain regions or points where the probability of finding it is absolutely zero. And you can say, well, how does it make sense for the particle that is continuously trapped in the box? We know it has a fixed momentum p. How does it make sense that that fixed momentum p, with fixed momentum p, can never be at certain locations if in fact it must be passing through those locations? And the answer is, I don't know. The answer is, the simplest way possibly to look at this is that the particle is no longer acting as a particle, it is acting as a wave. And even though the wave is interpreted as the probability of finding it, the solution tells us that it can never be at certain points. So the paradox, you might say, is that we have to live with certain unexpected results. And one of the unexpected results is that the probability of finding it at different locations will in fact be zero, even though the particle is moving back and forth. Now in the follow-up lecture, I will discuss more about the interpretation of these energy states and what we can do to confirm them. It turns out, for example, that we don't actually measure these probabilities, nor do we measure the energy levels. But what we can do is that if we have a system like an electron that's trapped in a potential well, and we hit it with a photon, then we can knock the energy level of the electron from here up to here, and by pumping energy in, and at some later time, it will fall back down and it will emit a photon. Right? Now the photon that gets emitted is going to be equal to the difference in the energy levels from where the electron began, which was energy E3, minus the energy E1. Okay? And by doing this sort of test, there are cases where we can measure the energy of the photons, and we can verify that the energies that I calculate from differences are observable and are consistent with the values of the energies that I've calculated. So with that, we're going to take up next time and continue for more discussions about the particle in the box, and also discussion about what happens when the height of the barrier is no longer infinite, but we will say it's finite. Okay, so at this point I am going to stop, and this will be the end of lecture 2 portion of chapter 41. In the sequence, it's probably lecture 15, but we will verify that, I think.
14.
What's that?
14.
14.
Yeah.
We'll verify that when it goes online. Okay, that's what we have for now, and we will continue next time.